An arithmetic function is any function with domain naturals. The codomain is usually real numbers, but sometimes it's complex numbers. All of the functions we talk about in this video have codomain integers. According to Hardy and Wright, an arithmetic function also expresses some arithmetical property of the input. One of the simplest arithmetic functions is the identity function. This function just returns the input back. Now let's talk about some more interesting functions. We'll start from the simplest functions and work our way up. The delta function is the simplest function we'll talk about in this video other than the identity function. It's officially called the Kronecker delta, named after Leopold Kronecker, who had a very large impact on number theory and algebra. However, this function is actually incredibly simple. It just returns 1 if the input is 1, and otherwise it returns 0. So why is this function getting its own section? Well, once we get to the Mobius function, we'll see that this function is actually very important to Dirichlet convolution. But before we get there, let's talk about some other functions. The next two functions we'll talk about are the number of divisors function and the sum of divisors function. These are denoted by the Greek letters tau and sigma respectively. These functions do exactly what you would expect them to do. We can use 10 as an example. The factors of 10 are 1, 2, 5, and 10. Since there's 4 of them, tau of 10 is equal to 4. Their sum is also 18, which means that sigma of 10 is equal to 18. We can also extend the sigma function by adding a subscript. Sigma subscript 2 returns the sum of the squares of the factors. So sigma 2 of 10 is 1 squared plus 2 squared plus 5 squared plus 10 squared, which is 130. Similarly, sigma subscript 3 returns the sum of the cubes of the factors. Now let's talk about one of my favorite functions. The next function we'll talk about is Euler's totient function, named after, of course, Leonhard Euler. This function is denoted by the Greek letter phi. The definition is that phi of n is the number of positive integers less than or equal to n that are relatively prime to n. Two integers are relatively prime when their greatest common factor is equal to 1. As an example, let's find phi of 12. Here we've listed out all the numbers from 1 to 12. Let's find each of their GCDs with 12. Now, here are the ones where the GCD is equal to 1. As we can see, there's 4 of them. Thus, phi of 12 is equal to 4. Now let's prove an important property of Euler's totient function. Here it is on the screen. This notation just means we have to iterate over all the divisors of n. We'll see this notation a lot in the future, so be familiar with it. If n was 10, for example, we would have to prove that phi of 1 plus phi of 2 plus phi of 5 plus phi of 10 is equal to 10. To prove this, we're going to use what's called a double counting argument. This is when you count a set in two different ways, and because it's counting the same set, the two different sums you get have to be equal. This is a very common type of argument in combinatorics. The set we're going to be double counting on is this set, that is, the set of all rational numbers greater than 0 and less than or equal to 1, with denominator n. First, notice that the size of s is equal to n. This is because the numerator can be any integer from 1 to n inclusive. Now, as you may expect, we're going to prove that the size of s is also equal to the left-hand side of the equation we're trying to prove. First, we'll simplify every fraction in s. Here's the example for n equals 10. Now let's group the fractions in s by denominator. Here they are sorted by color. Now think about this question. How many positive fractions less than or equal to 1 are there such that when simplified, the denominator is some positive integer k? So for example, as we can see, for k equals 10, it would be 4, because we have 1/10, 3/10, 7/10, and 9/10. Well, a fraction has denominator k when simplified, if and only if the numerator is relatively prime to k. Thus, we need to find the number of integers between 1 and k inclusive that are relatively prime to k. This should sound familiar. By definition, this is just phi of k. Now let's look at which denominators are present in s. Well, the set of denominators in s is exactly the set of divisors of n. Thus the size of s is equal to the sum of the phi function of the divisors of n. But the size of s is also equal to n, so this means that we're done. Now we have one more function to talk about before we get to Dirichlet convolution. The last function we'll talk about is the Mobius function, named after August Ferdinand Mobius, who you might know from the Mobius strip. The Mobius function is denoted by the Greek letter mu. The definition of the Mobius function involves square-free numbers. A number is square-free if it's not divisible by any perfect squares except for 1. If the input n is square-free, we return 0. Otherwise, we have to look at the prime factorization of n. Here's a general formula for a prime factorization. However, since n is square-free, all the exponents are equal to 1. Thus, n is the product of many distinct primes. If there's k primes, we return -1 to the kth power. Here are some examples of the Mobius function. For example, the prime factorization of 10 is 2 times 5. Since 10 is square-free and there's 2 primes, we return -1 squared, which is 1. Now we prove an important property of the Mobius function. Here it is on the screen. Again, this notation means that we add over all the divisors of x. First, we claim that we can replace all the exponents greater than 1 and replace them with 1. We can use 2520 as an example. We claim that we can replace it with 2 times 3 times 5 times 7. To prove this, consider a divisor that would be removed. That is, some number d that's a factor of 2520, but not 2 times 3 times 5 times 7. Then it must have an exponent that's greater than 1. So what is mu of d? Well, by definition it's equal to 0, so we can remove it with no problem. To finish the proof, we need to introduce the concept of A choose B. This is just the number of ways to choose B items from A items, where order doesn't matter, and it's denoted by this symbol. Now let's express the left-hand side in terms of these. If a number has 0 prime factors, then it must be 1, and the Mobius function of it is -1 to the 0th power, so we have 1 times k choose 0. Then, if there's 1 prime factor, then the Mobius function is -1, so we subtract k choose 1. Similarly, add k choose 2, and so on. Now to finish, we need to use the binomial theorem. We won't prove it here, but if you haven't seen the proof yet, I suggest you look into it after the video is over. Anyway, the binomial theorem tells us that this sum is equal to 1 minus 1 to the kth power, which is obviously equal to 0. Thus, we are done.